Amazon Aurora. Design considerations for high-throughput, cloud-native relational databases. Abstract. Amazon Aurora is a relational database service for OLTP workloads offered as part of Amazon Web Services. In this paper, we describe the architecture of Aurora and the design considerations leading to that architecture. We believe the central constraint in high-throughput data processing has moved from compute and storage to the network. Aurora brings a novel architecture to the relational database to address this constraint, most notably by pushing redo processing to a multi-tenant scale-out storage service purpose-built for Aurora. We describe how doing so not only reduces network traffic, but also allows for fast crash recovery, failovers to replicas without loss of data, and fault-tolerant self-healing storage. We then describe how Aurora achieves consensus on durable state across numerous storage nodes using an efficient asynchronous scheme, avoiding expensive and chatty recovery protocols. Finally, having operated Aurora as a production service for over 18 months, we share lessons we've learned from our customers on what modern cloud applications expect from their database tier. Keywords in this paper are databases, distributed systems, log processing, quorum models, replication, recovery, performance, OLTP. Section 1. Introduction. IT workloads are increasingly moving to public cloud providers. Significant reasons for this industry-wide transition include the ability to provision capacity on a flexible, on-demand basis, and to pay for this capacity using an operational expense as opposed to capital expense model. Many IT workloads require a relational OLTP database. Providing equivalent or superior capabilities to on-premise databases is critical to support this secular transition. In modern distributed cloud services, resilience and scalability are increasingly achieved by decoupling compute from storage, and by replicating storage across multiple nodes. Doing so lets us handle operations such as replacing misbehaving or unreachable hosts, adding replicas, failing over from a writer to a replica, scaling the size of a database instance up or down, etc. The I/O bottleneck faced by traditional database systems changes in this environment. Since I/Os can be spread across many nodes and many disks in a multi-tenant fleet, the individual disks and nodes are no longer hot. Instead, the bottleneck moves to the network between the database tier requesting I/Os and the storage tier that performs these I/Os. Beyond the basic bottlenecks of packets per second, PPS, and bandwidth, there is amplification of traffic, since a performance database will issue writes out to the storage fleet in parallel. The performance of the outlier storage node, disk, or network path can dominate response time. Although most operations in a database can overlap with each other, there are several situations that require synchronous operations. These result in stalls and context switches. One such situation is a disk read due to a miss in the database buffer cache. A reading thread cannot continue until its read completes. A cache miss may also incur the extra penalty of evicting and flushing a dirty cache page to accommodate the new page. Background processing, such as checkpointing and dirty page writing, can reduce the occurrence of this penalty, but can also cause stalls, context switches, and resource contention. Transaction commits are another source of interference. A stall in committing one transaction can inhibit others from progressing. Handling commits with multi-phase synchronization protocols such as two-phase commit, or 2PC, that's challenging in a cloud-scale distributed system. These protocols are intolerant of failure, and high-scale distributed systems have a continual background noise of hard and soft failures. They are also high latency, as high-scale systems are distributed across multiple data centers. In this paper, we describe Amazon Aurora, a new database service that addresses the above issues by more aggressively leveraging the redo log across a highly distributed cloud environment. We use a novel service-oriented architecture with a multi-tenant scale-out storage service that abstracts a virtualized segmented redo log and is loosely coupled to a fleet of database instances. Although each instance still includes most of the components of a traditional kernel, query processor, transactions, locking, a buffer cache, access methods, and undo management, several functions are actually offloaded to the storage service. We offload redo logging, durable storage, crash recovery, and the backup restore functionality. All those things are offloaded to the storage service. Our architecture has three significant advantages over traditional approaches. First, by building storage as an independent, fault-tolerant and self-healing service across multiple data centers, we protect the database from performance variance and transient or permanent failures at either the networking or storage tiers. We observe that a failure in durability can actually be modeled as a long-lasting availability event, and an availability event can be modeled as a long-lasting performance variation. A well-designed system can treat each of these uniformly. Second, by only writing redo log records to storage, we're able to reduce network IOPS by an order of magnitude. Once we removed this bottleneck, we were able to aggressively optimize numerous other points of contention, obtaining significant throughput improvements over the base MySQL codebase from which we started. Third, we move some of the most complex and critical functions like the backup function and the redo recovery function from being one-time expensive operations in the database engine to continuous asynchronous operations amortized across a large distributed fleet. This yields near-instant crash recovery without checkpointing, as well as inexpensive backups that do not interfere with foreground processing. In this paper, we describe three contributions. 1. How to reason about durability at cloud scale, and how to design quorum systems that are resilient to correlated failures. We deal with that in section 2. 2. How to leverage smart storage by offloading the lower quarter of a traditional database to that tier. Section 3 is where we talk about that. And 3. How to eliminate multi-phase synchronization, crash recovery, and checkpointing in distributed storage. Section 4. We then show how we bring these three ideas together to design the overall architecture of Aurora in section 5, followed by a review of our performance results in section 6 and the lessons we've learned in section 7. Finally, we briefly survey related work in section 8 and present concluding remarks in section 9. End of section 1, Introduction.